In this video, we will talk about how to compute second-order partial derivatives. All right, so first I want to introduce some notation to talk about second-order partials. So if we take del x, so the partial with respect to x, of del f del x. So we're taking the partial derivative twice, but with respect to x. So we'll notate that in two ways. We'll either write del 2 f over del x2. So that's one of the notations for a second partial derivative with respect to x. Or the other way is we'll write f x x like this. So that means we've taken the partial with respect to x and then with respect to x again. Okay, so if we write del x, if I take the partial with respect to x of del f del y instead, we can write that in two ways as well. I can write that as del 2f, and then over, and on the denominator I just stay consistent with that order. So I'll write del x, and then I'll write del y to stay consistent with the order that I had written it in here. So what this means is we are doing the partial with respect to y first. So the partial with respect to y first. I think it's easier to see once it's written in this notation, because this means definitely do the partial of f with respect to y, and then after we did that, then we took the partial of that with respect to x. So we did it with respect to x second here. And using our other notation, we would write this as f y x like this. So in this notation, the subscript that's written first is the partial we do first. And the subscript that's written second is the partial that we do second. All right. And we can similarly define the other second order partial derivatives. So I could also do del 2f del y2 in this sort of way, and del 2f del y del x. I could also define them in a similar way. All right, so let's do an example. All right, so in this example, let's find all first and second order partial derivatives. Okay, so first let's find all the first order ones. So that's HA and that's HB. And then the second order ones, so there's a few of these. There's HAA, there's HBB, there's HAB, and there's HBA in the opposite order. Okay, so we have to do all 6 of these. All right, so let's begin with HA, the partial derivative with respect to A. So taking the derivative of this ln portion, I'll use chain rule. I'll get 1 over 3a minus b. And then I have to multiply that by the derivative of the inside with respect to a. So when I do that, I'll get 3 for the derivative of 3a. And the b gets treated as a constant, so that's just 0 for that. Okay, and then for the derivative of the next part, a squared to b to the 5, b to the 5 gets treated as a constant. So I'll end up taking the derivative of a squared, and I'll get plus 2a b to the 5. All right, so that is my partial derivative with respect to a. All right, so 1 out of 6 done. Now let's do the partial with respect to b. So the derivative of the ln portion is going to be 1 over the inside, using chain rule, 3a minus b. But multiply that by the derivative of the inside. With respect to b, so 3a gets treated as a constant, and that derivative is 0. And the derivative of minus b is going to be negative 1. And then a squared is going to get treated as a constant. So I take the derivative of b to the 5, and I'll get the 5 comes down, and I'll get 5a squared b to the 4. And that is my partial derivative with respect to b. All right, now let's start doing the second order partial. So let's do HAA next. So I have to take HA, this first partial derivative I did, and do the partial again of that, but with respect to the variable a. So to take the partial of this now, again, it's going to be helpful if I rewrite this fraction as 3 times, and I'm going to move the 3a minus b up to the numerator. So when I do that, I get 3a minus b to the negative 1. If I do that, I won't have to use quotient rule when I take this derivative, and that'll be a bit quicker. All right, and next I'll just keep it, next term I'll keep the same, 2ab to the 5. All right, so now we're ready to take the partial derivative of this with respect to the variable a. All right, so I need chain rule. The negative 1's going to come down, and I'll get negative 3 times 3a minus b to the negative 2. Multiply that by the derivative of the inside with respect to a, which is 3. And then the b to the 5 is going to get treated as a constant. And the derivative of 2a is just going to be 2. So we'll get 2b to the 5. And I could simplify this a bit. Whoops, let's write that 5 better. 2b to the 5. This equals negative 9, 3a minus b to the negative 2 plus 2b to the 5. Let's write that 5 better. All right, so that is my that is HAA. So we just took the partial with respect to a twice. Now let's do the partial with respect to b twice. So with respect to b twice. All right, so it's going to be helpful if I take HB and I rewrite this as negative parentheses 3a minus b to the negative 1 plus 5a squared b to the 4. So taking the derivative of that, partial derivative of that with respect to b, I need chain rule for this first term. The negative is going to come down and I'll get a positive, and I'll have 3a minus b to the negative 2. Multiply that by the derivative, the partial derivative of the inside with respect to b, which is going to be negative 1. And the derivative of the next term, partial derivative of the next term with respect to b, I treat 5a squared as a constant. The 4 is going to come down, it'll multiply the 5, and I'll get 20, so plus 20, a squared b cubed. All right, and that is my partial, that is this second partial order. Sorry, I mean that is this second order partial derivative. Okay, so simplifying this a little bit, I could write this as negative 3a minus b to the negative 2 plus 20a squared b cubed. All right, so that is this one. All right, so we have 2 more to do. All right, so next let's do HAB. So what this means is do the partial with respect to a first, and then take the partial with respect to b afterwards. All right, so I'm looking at the partial with respect to a, which was up here, and I'm going to take the partial of that with respect to b now. So I need chain rule for the first term. Negative 1's going to come down. I'll get negative 3 times 3a minus b to the negative 2, and multiply that by the partial of the inside with respect to b, which is negative 1. And then the derivative of the next term, the partial derivative of the next term with respect to b, 5 is going to come down, and I'll get plus 10a b to the 4th. And simplifying this, negative 1 multiplies negative 3 to give me 3, positive 3, times 3a minus b to the negative 2, and then plus 10a b to the 4th. And that's our answer for this one. So one more to go. We also need to do HBA, and this means do the partial with respect to b first, and then take the partial with respect to a after that. So I'm going to be looking at my partial derivative with respect to b, which was here, and now, whoops, okay, so that was our partial with respect to b, and then taking the partial derivative of that with respect to a. So I need chain rule for the first term. Negative 1's going to come down and give me positive 3a minus b to the negative 2. Multiply that by the partial derivative of the inside with respect to a, which is 3. And then the partial derivative of the next term with respect to a. The 2 is going to come down, and I'll get plus 10a. b to the 4th stays there. That's just a constant multiplying it. All right, and that is 3 times 3a minus b to the negative 2 plus 10ab to the fourth. It's actually, let me make sure that my box doesn't cover up that exponent there. I'll just spread it out a little bit. So one important thing that I want to notice about these is the answers to the last two were the same. So this was the same as that. So that, it turns out these mixed partials, so when you take the partials with respect to different variables, even if you switch the order, it turns out they will be the same. Okay, so I want to state this as a theorem. So the theorem says, if our original function f and the following partials, so the partial with respect to x, with respect to y, and then if I take these mixed partials, f of x comma y and f of y comma x, if these are all defined on an open region containing some point that we're interested in evaluating the derivative at, a comma b, and if they're all continuous at that point, then these mixed partials, so whether I do the partial with respect to x first and then y, or if I do the partial with respect to y first and then x, they are going to be the same. So these are called mixed partials because they involve different variables. Mixed partials. All right, in terms of our goals for this section, we have now done a bunch of examples where we computed partial derivatives. First order partial derivatives in the last video, and this video, first order and second order partial derivatives. And we stated Clairaut's theorem. Clairaut's theorem was the name of this theorem that says, oh, these mixed partial derivatives are going to be equal as long as these conditions are true. And in most situations, these conditions are true. So in the next video, we will do an example where we use partial derivatives to approximate the change in a multivariable function.